One more very common method of implementing Boolean functions in not in digital logic in general, but it is used in many FPGAs and so on. Okay, the idea is known as a lookup table. What is a lookup table? It's essentially a memory. Okay, if you remember, when I spoke about a decoder, I said the following is true. Okay, so I have a decoder here. Okay, n is to 2 power n decoder. This is my n inputs, 2 power n outputs, my address lines, and depending on which so here for example row 0 will go here, row 1 will go here, and so on like this. Okay, this is row 0, 1, 2 power n minus 1, right? And essentially I have the enable signal of my decoder here, which invariably would be tied to VDD. Okay, and now this lookup table is essentially a memory. So if you give an address, this decoder will turn on exactly one row at a given time, right? And it is going to read out some particular row value from there. Okay, so let us assume that there are k such bits, 1, 2 like this to k minus 1. Okay, so I have k bits, b0, b1, b k minus 1. Okay, I have k bits which are coming out of each row depending on their decoder address. Okay, so my address bits are like this, a n minus 1 all the way to a0 n bit. So I have an a n minus 1 to a0 bit address, right? Right, and depending on the combination, one of the rows will turn on and I will read out k minus 1 b k, I mean all the way down to b naught, k bits of information will be read out. Okay, this is the idea. So for example, if my address was 000 and the data that is being stored in this memory is like this, okay, then when I give the address 00000 and say read, okay, 000111 will be read out. Okay, on the other hand, if I had this and I gave an address sequence of 0000 A0 being equal to 1, okay, only that bit being 1, then I would read out the magenta value 11000 would come out from this, basically from this memory. Okay, now what this allows us to do is to go ahead and implement arbitrary Boolean functions again. Okay, so let us see what this actually how to implement this. Let us say I have an n bit address, okay, which means there are 2 power n locations and a k bit readout from that memory, right? So and for our example, let us assume that n equal to 3 and k equal to 1. The very trivial case I am talking about, which is basically it's an array, it's not even a memory, it's not even a two-dimensional memory. Okay, it's only one bit that I can store like this. okay, and I have a decoder like this, which is 3:8 decoder. Enable is 1 and I have the select lines here. Yeah, and I am going to read out just one bit, B0, A2, A1, A0. Okay, now let's go back and look at the XOR 3 function that we wanted. Okay, so let's look at this. Let's look at this function that we had spoken about earlier, and we'll see how to implement this again in our lookup table. Okay, so I have 0, 1, 2, 3, 4, 5, 6, 7. So let me add the 8th column. Okay, I am going to take this. Yeah, right. So now what am I trying to implement? I am trying to implement this function here. Okay, so you see that all I have to do is simply connect A2 to A, A1 to B, and A0 to C. Now if I did that, then when ABC is 0, 0, 0, row 0 will get activated, and in that location I simply need to load this particular truth table value. So 0, 1, 1, 0, 1, 0, 0, 1. Oh, I already had the 8-bit, sorry. Yeah, okay. So all I had to do was to simply load this and I would get my B0 is what I would call as Y XOR 3. Now if I had an other column, right, there's no hard and fast rule that I should have only k equal to 1, right? I can have more than 1 bit coming out of the memory, okay, from this lookup table, right? And therefore I can just say I will load the next function, which is 0, 0, 1, 1, 1, 0, 0, 0. So that means, assuming k equal to 2, this is B1. I am saying this is what I will call as Y. Okay. So as usual, just like the case of the decoder and the multiplexer, it was very straightforward. Simply take that particular truth table value that you want and load it into the memory, into the lookup table as it is, and allow that to be read out in order to get this XOR gate working correctly. Okay, so with that, I will conclude this discussion on the idea of implementing arbitrary Boolean functions using multiplexers, decoders, and higher level circuits, right? And like I said, this is very commonly used in FPGAs. Okay, the field programmable gate arrays, right? The idea is to the idea is you given a logic, you can program the functionality on a hardware. Each time you want a new logic, you can program it differently. So this kind of logic is not implemented using elementary logic gates. Okay, they are implemented using these lookup tables and other such techniques. Thank you.